So hello and welcome everybody. Good morning, good afternoon, good evening, wherever you might may be. Thank you for joining us. This is the Omdena Silicon Valley Chapter. And today we are presenting to you our final results from our 4-week challenge on extreme weather forecasting. We have two presenters today from my team, Vishu Kailer and Kseniya Trusova. They've both been active in leading the tasks on EDA feature engineering as well as modeling. So they will share our findings and results from the last few weeks over with you. This is a chapter which is a part of Omdena in Silicon Valley in California. And if there is interest for you to join the chapter where we take on various challenges related to social good. It could be weather, it could be healthcare, it could be disaster response, and many other projects. We also encourage people to network and connect like-minded people together. So if there's interest in joining this chapter, please feel free to find us on LinkedIn, or you can also find us in the Omdena Silicon Valley Slack link. If you want more details, please ping me and I will share details with you if you want to join in. So with that, we'll get started. Let me introduce you to my two speakers of the day. As I mentioned, Vishu. We'll start off with Vishu since he's been working on EDA and feature engineering. He is a university student in the second year in an integrated master's program in AI and machine learning. He has many projects on deep learning and machine learning techniques over the 2 years, and he's worked in various domains like deep learning, NLP, computer vision, and so on. So welcome, Vishu, and thank you for presenting. And our next speaker is going to be Kseniya Trusova. She has over 10 years of experience in avionics. Several years ago, she interested in expanding into the data science. So she started developing her skill, and now she works for a high school of a polytechnical university in her city, developing her data science skills. So, and she's interested in collaborating and working with projects, real world projects, to impact and help people. So welcome to you both. And with that, I'll get started. I have the presentation going, and I will scroll along as you go along. Okay, with that, Vishu, you want to take it on?
Sure, ma'am. Thank you, everyone. Greetings of the day. This will be a final presentation regard to the Omdena Silicon Valley chapter for extreme weather forecast. As per the supervision of a chapter lead, Nishan Kachwal, this presentation is the collaboration of every individual in a team who has given their insights, their efforts, their time, and have been keenly motivated in giving their best to this particular project. Because of them and our entire team as a whole, this project has been a great success. Moving forward, next slide, please. Yes. Now coming to the problem statement. Since we know for a particular region, there is an extreme swings in temperature and precipitation, such that there is drastic change and which is non-periodic in nature over even a small region. So this causes an immediate need for long-term forecasting models. We also know that there are many models regarding weather prediction, and all of them are physics-based, or they use like geographical analysis for a particular locality and try to predict the weather. But the physics-based and geographical-based analysis has certain limitations and many boundary conditions, due to which it cannot accurately predict the weather for every particular, you can say, locality, region, or for every particular time and area. So since we have an availability of meteorological data, we, the data scientists, can improve the weather forecasting by blending it with the physics-based forecasting model to improve the accuracy by a huge amount. Moving forward. Now coming to the data. So having a little bit of insight in beforehand, so we have received the data from the WIDS, which is Women in Data Science. in collaboration with the Climate Change AI, CCAI, there is weather and climate information to a number of US locations. Like we have many locations of the United States, and we have been provided with the weather and climatic information, which include temperature, precipitation, humidity, sea level pressure, and many more factors, along with the El Nino parameters for a given set of locations as per latitudes and longitudes for the United States. Also, the temperature, pressure, and various other factors have been given for many weather stations currently present in the US. So we have around 9, we have around 9 weather stations in the data set, and one particular for the mean. Each row in the data corresponds to a single location and a single start date for the 2-week period. So each row in the data set is for a single location and for a specific latitude and longitude, and it corresponds to a single start date for the 2-week period. Now, the task is for the prediction involving forecasting sub-seasonal temperatures over a 2-week period within the United States for each location and start date. Moving forward. Now, there are many tasks which we have performed over the data set, and they are in a sequential fashion. Like first, we perform the data preprocessing, in which we preprocess the data, obtain the few null values which were there in the data set, change the data types from object to integer or float so that they could be trained. Then we perform the exploratory data analysis, also termed as EDA for short, in which we performed various visualizations and calculated, like probability distribution curves and various other things. Then we perform feature engineering to check for the relevant columns which have a significant impact over a target variable, which is the temperature. Then we did the model evaluation. We run various models on the trained data set to predict the changes in temperature for the test data set. Moving forward. The first one is the data preprocessing. In data preprocessing, there were few things which were most significant, like the null values. Obtaining null values by imputation and other approaches. It was one of the most important things which we could do in the time series data, because if there is any one value which is missing in time series data, it could lead to many disorders in evaluation or prediction. And then we preprocess it. We preprocess the data and make the data set ready for analysis. Before analysis or the exploratory data analysis, we have to perform many things. Like we have to convert the object data types into the integer data types. We have to remove the index. We have to take out the null values as well, evaluate them, and then we can proceed with the exploratory data analysis. Moving forward. Yeah, so this is, you can say, a matrix of all the missing values. There were a few missing values in the data set, and most of the missing values were of specific columns and time frame, here referred to as months. You can see various empty regions in that particular matrix, and those empty regions are the missing values. And if you divide the matrix horizontally into 2 parts, since the data which was provided to us was of 2-year range, we can see that they are pretty almost lying within the same month. Like for one, it is lying in October 2014, and for one, it is lying in October 2015, and something like that. So it is a case of NMAR, not missing and random, that the values which are missing, they are not randomized. They are in a order or in a fashion, or they are periodic. And the methodology we used many imputers like mean imputer, median imputer, most frequent, and Kenan imputer to extract the null values. And then we took the best out of them. Moving forward. So this was the proposed solution for the data preprocessing. In the first step, we checked in which columns are the missing values. The missing values were mostly in the precipitation column, which were for the CANCOM and CCSM weather station. So then we checked on which indices are the missing values changing. So for which indices or for which date or month there were missing values. And then we evaluated the null values with the help of various imputers, and we took the best one out of it. Moving forward. Then comes after the data is entirely pre-processed, and it is then proceeded with the exploratory data analysis, in which we first do the analysis. The analysis of data set is crucial for model development and training, because analysis gives us insight about data. Like how is one variable dependent on other? What is the probability distribution curves? How is everything changing? Like what are the mean, median, standard deviations, and many more things. Like what are the intensity points? And then all these things are better represented in form of visualizations. You cannot directly calculate the mean and standard deviation by just looking at the numbers. You cannot predict, you can say what is the dependency of one variable over the other by just seeing the numbers. One needs a visualization. So visualization is an integral part for exploratory data analysis. Next slide, please. So here are a few graphs which we were done in the exploratory data analysis, like distribution of climatic regions. The distribution of number of data points in terms of region is uneven. As you can see in the lower graph, in the lower left corner, the regions which have the most data point is the BSK one. It has around, let's say, about 50 to 49% of the entire data points. And all of the regions have pretty low data point as compared to that of the BSK one, such that the data is not uniformly distributed in terms of regions. It is skewed towards the BSK region. And similarly, when you have a look at the graph on the upper right corner, it gives the analysis of weather station for temperatures. The mean and deviations of all the weather stations is almost similar. There you can see we have around 9 weather stations, and the last one is the ensemble mean, the collective mean of all the 9 weather stations. And they have the mean and standard deviation almost same. Like the blue bar represents the mean and the red bar represents the standard deviation. They are almost lying in the same zone, such that the weather stations computed the temperature with almost the same accuracy. Moving forward. Then we did the feature engineering and the exploratory data analysis with the correlation matrices as well. Like matrices were also used to compute the irrelevant factors. Like in the matrix down below, you can see a value of 0.96 or 97, which is corresponding to height 500 and height 100. Like they're very well correlated. So we can take any one of them and exclude the other one for the model development of feature engineering part. And similarly, in the above graph, you can have a look like the mean prestige for 4 to 6 weeks and the mean precipitate of 3 to 4 weeks. They are pretty same, like they have a correlation of 0.99. So we extract one of them for the model development and remove the rest. So that's how the correlation matrices are used. Moving forward. Yes. Then we did the density counter maps. The counter maps were used to check the intensity points and distribution of variables. Like in the lower left graph, you can see the data is distributed for a pretty wide range, and it is in a central patch of region, the yellow zone, which you can see. And similarly, if you look at the above graph, like in the top right corner, you can see the data is distributed in form of 2 peaks. Like one peak is lying between 16.2K to, let's say, 16.4K, and the other peak is lying between 16.6K to 17K, such that with the counter maps, you can get an idea like how your model will work, because counter maps give a little bit of insight about the gradient descent as well, like how your model is going to train. If the data is evenly spread, the model is going to train pretty slow. And if the data is like not evenly spread, it has maximum points within a peak or within a shallow region, then your SDG or the stochastic gradient descent is going to learn pretty fast. So counter maps gives us this insight as well. Moving forward. Then, since we had a data set which had a large number of rows, so to perform more influential exploratory data analysis, or the EDA, we performed it by splitting the data sets by various influential factors, such that the data set was split into the following clusters. They were split into seasons, like the 4 seasons, the year, and the regions as well. And you can see in the above graph as an example, like the temperature distribution in winter season on the basis of latitude. Now, this is a graph termed as a Voiland plot. The Voiland plot gives us a much more mathematical intuitions, like it gives us the standard deviations, the mean, the variance, the outliers as well. Like if you look at the left-hand side of the graph for the latitude value of 0 to 0.2, they are pretty widespread. Like you can see the thickness of the volume plot is pretty more as compared to that of latitude 0.8 to 1. They are pretty slim and thin. Also, you can see the outliers as well for a latitude value of range 0.45 to latitude value of 0.65. We have a large number of outliers or data points arising out from the regular data. So it gives us the insight as well, like which particular set of values have the outliers and which particular set of values do not have the outliers. Moving forward. So then we even performed the feature extraction as well. The heat maps and counter maps were widely used for feature extraction and eradicating irrelevant columns. As you can see in the above graph, we use the heat map, and in the lower graphs, you can see the counter maps used for feature extraction, such that feature extraction helps us to take the more relevant columns, which are more dependent on the target variable, and to remove the irrelevant columns, which are not dependent on the target variable. Moving forward. Now I would like to ask Kseniya Trusova, my colleague, to continue forward.
Thank you very much. Thank you. Hello, everyone, and happy to have you here. And I would like to present the modeling steps which our team has gone through and our learning process. And first of all, we made the literature research about what models are used for the temperature prediction problem by other researchers. Based on these results, we choose the model of the type of the model, and then we worked on building and evaluating the model by found tutorials. Next slide, please. According to the literature review, the most popular model is LSTM, long short-term memory. Besides, we found enough useful tutorials to build it. And you can see these links on the slide. And that is why we decided to try LSTM. Next slide, please. What is LSTM and how does it work? Long short-term memory networks are a special kind of recurrent neural networks capable of learning long-term dependencies. They were introduced in 1997. The LSTM has the ability to remove or add information to the cell state, and regulated by structures called gates. You can see it on the scheme. Gates are a way to optionally let information through. They are composed out of a sigmoid function and a point-by-point multiplication operation. And LSTM has 3 of these gates to control the cell state. At the forget gate, a sigmoid decides what information should go through away from the cell state. And at the input gate, a TAN function creates a vector of new candidate values that could be added to the state. At the output gate, the cell state passes through TAN function and is multiplied by the output of the sigmoid function. It is a short background. And next slide, please. First of all, we thought about the architecture of the model. Literature review helped us again. Here you can see parameters the most used the most often. You can see these 5 hidden layers and 16 neurons, sigmoid and ReLU activation functions, and others. And based on this, we came up with our own configurations to experiment with. We took 13 hidden layers and 128 neurons, TAN, sigmoid ReLU, and softmax activation functions, and 1030 epochs, 721 window size, and 16256 batch size. And I would say that the optimal window size is 7 and the batch size is 16 according to our results. Next slide, please. This slide shows how we evaluated the model. It is not the best result we got, but it makes sense. We considered 6 features according to the correlation coefficients after the EDA, and you can see the correlation matrix on the slide. And then we scaled the features, transformed the data set by sliding window, which size is 7 days, as I said, and put it to the input of the model. We computed the loss function, root mean squared error, visualized the loss for training and validation, and you can see it here on the figure, these blue and red lines. And then we visualized how the model predicts the average value of minimum and maximum temperature for the next 14 days. This is top graph. Red points are predicted by the model. And then we visualized the distribution of an absolute error just to compare this difference between predictions and true values. Next slide, please. So what have we observed from the experiments? About layers changing. If we increase the number of layers, we get a better accuracy. But after the 4th layer, the accuracy decreases. About neurons changing. 50 is optimal for 1 layer, but changing the number of neurons doesn't influence 2-layer and 3-layer accuracy and loss functions so much. What we have observed, activation functions changing. ReLU is optimal for 1 layer, and different activation functions for different layers perform better than the same. So we also got some results with our loss function and accuracy. You can see it on the slide. And this is our findings. I think that the more experiment, the more experiment we can manage, the more information we can got, of course. And this is our findings. And next slide, please. And I would like to say a couple of words about how to improve the model. Our domain expert, Li Chengzhen, recommended including weather models predictions as different weights can be assigned to different models based on regions, locations, and seasons. You can see this models list on this slide. And another potential improvement is to clarify the work with different locations, because now we switch on between locations and it would be good to use all locations, of course. These are the directions of further work. And next slide, please. And that is all that I wanted to say. And I would like to thank the team for their support, Vishu, Irui, Lechenk, Nisha, Tekel, and others. Thank you very much, guys, for the great experience. And thank you very much, Nishin, for this great opportunity to learn, collaborate, and contribute. And thank you very much, everyone, for your attention. Thank you.
Thank you, team. Thank you for the wonderful presentation and all your hard work. The 4 weeks went by very fast, and I'm very happy to see the kind of collaboration and and teamwork that we did together in the last few weeks to get the model up and going. And I'm sure there was plenty of learning on our part, how each of these factors, because there's so many factors that influence a model's outcome. So to learn each of them and go through each of them and understand them, that's building a great foundation for future machine learning projects, right? So thank you for that again. I want to thank, of course, the entire team for participating, showing up in task meetings, no matter how early or how late it was for you. You guys showed up, you guys did the work, you guys shared your work, you taught each other, you learned from each other, and that's what it's all about. So that is what I aim for my chapter, is that everybody comes and learns something from each other and has something to share. And I hope that by doing that, we tackle also projects which make impact, like some impact, like this is something very challenging, as you may see in different parts of the world. Weather has become very much at the forefront in terms of news. There's floods, there's extreme weathers, which kind of influence all of us in a negative way. So to make better predictions basically just helps people to react to these extreme events in a much better way. And we took a small step going forward in trying to help that prediction. So I thank you for all your efforts. And of course, my chapter is always open. We will continue to work in Slack. If you guys want to continue to, I know some of you have asked for us to continue, so we will continue the Slack till you have, till you decide to leave. It'll be open, and in the future, please look out for new projects. I'm always looking out for suggestions. If you have anything in mind, feel free to ping me. And yes, this presentation will be put up on our YouTube channel with a link, so you can always go back and refer to it. And feel free to ask the team any questions if you may have now. So I'll keep the mic open if anybody has any questions, or if anybody wants to make a comment or say something.
In addition, this is Bipul,
Hi.
and thanks to Vishu and the Kseniya. So it's quite a good presentation, and I think it's quite elaborative. They have described into the process they followed and the approach, as well as the both the theoretical and practical approach. So that's a very good presentation. Thank you guys for the hard work and good work which people have put up into that one.
Yeah, I concur. All right. Any other questions?
Yeah, I would also like to thank Xtreme for organizing the challenge. And I would like to thank Vishu and Kseniya for the nice presentation. I didn't contribute much to the final result, but I really learned a lot from discussing with you. Actually, I'm a freshman to deep learning before I joined this local chapter, but now I can perform the LSTM by myself. So I really appreciate this journey. And I have a few questions for Kseniya and also for Vishu. And in the latter part, which is the modeling part, this is something about technical questions. So first question is that Kseniya introduced that the units, number of units, or the neurons in different layers. I have just a question: how did you determine the best results? And I suppose it depends on the size of the input layer. And so the question is, what is the size? What is the size of the input layer? And if you change the size of the input layer, does the units number also need to change? I mean, by a lot, or the result does not change much? This is the first question. The second question is that I'm just confused. You mentioned you use tangent H function, a sigmoid function, a ReLU function, and activation function. So which one is the best? In one slide, I cannot remember the definite number, but I remember that in one slide you mentioned that tangent H function is the best. I think that depends on whether you standardize the input or normalize the input. So could you give a bit more details on how did you process the data?
Sure.
So
Thank you very much.
Yeah,
Okay.
yeah.
Thank you very much for the questions, Cenk. And the first question, the size of the input is 7. As I said, this was 6 features, and we put 7. Our size of the input is 7, and yes, I provided some empirical formulas in our channel how to define the number of neurons according to the number of size of the input size, and according to this, I tried to estimate and how many neurons we should put in each layer, and this is for my suggestions and team. But we discussed it in the team, and I think that this way we moved forward, and if it makes sense.
Yes. So, did you try use like more than 7 input size, like 14? I remember you suggest use 7 to 15 or 7 to 14. So if we increase the input size, will you have to increase the units and number of neurons?
Sure. Yes, we should do it according to our empirical formulas and how we can define this the size of the number of the neurons, and of course I think it influences.
Do you think it has a huge impact from your experience?
To be honest, I don't know. This is my first experience with it. Yes, and
Sure.
but I think it is. I guess that it show. Of course,
Yeah.
I think that the knowledge we can get from experiments. Mm-hmm.
Yeah, I agree with you. Generally, it should have a huge impact, but for this specific project, it is a subseasonal prediction. I do not know whether it really helps, but I agree with you that generally it should help.
Yeah, I think it would be a good thing to explore this, right? So we had limited time,
Sure.
right? So we couldn't do all the experiments, but we are off to a good start where we know kind of which factors to play around with. So maybe as a next recommendation to take the model forward, you could try doing that experiment of increasing the number of input layers and seeing how that influences the number of neurons and then accuracy. And I think you had a second question about using different activations,
Activation
right?
function. Yes.
So Kseniya, did you have any input or
Sure.
Go ahead. So
yeah. Can you go back to the slide which details
sure.
the activation function?
It would be convenient.
Here?
Yes, I guess. Yes, this is for.
Previously, you have
our...
another one in the. Okay. Please.
Let's see. This one? No, this is. I think this is the one.
Probably next. Yes, next.
She talks about the
descriptions.
activation functions.
Yes, and here we can see that for the one layer, the best results was the ReLU activation function, and it was probably we got this result for the one layer, and but I think we didn't have enough time to check 2 layers and 3 layers with the best combination, the best model, because a lot of we should pass a lot of variations, and here for 2 layers, I would say, and for 2 and 3 layers, I would say that the different activation functions. I think that we have this information on the slide that changing the functions and this doesn't influence to the loss function, and it doesn't influence the loss function and probably the accuracy too so much. This is
Thank
from
you.
our findings, yes, at the current stage. But I think that probably if we proceed our experiments and if we continue, I think probably we will be able to get other results, probably.
Okay, thank you very
Yes.
much. So from my
One thing I would
experience,
like to say as well.
Sure.
Yeah. As Mr. Lishing asked, like, which activation functions would be best? And actually, the activation functions for this particular data set do not change the accuracy that much. Like, the accuracy changes drastically when you increase the layer. As you can see, for the first layer, we have 62%. For the second one, we have 41. And for the third one, we have 52. So it does matter like which activation function you use, but you can say the number of layers or the increase in layers bypasses the change of activation functions. So this is one thing which we drew from the data set while running the 3 layers. And also, as soon as we change the number of layers from 3 to 4, no matter which activation function we use, the accuracy doesn't rise above 46%. So this is one more thing which I would like to add.
So I
Thank
think
you.
okay.
I can make a comment here that the choice of the activation function for each of the LSTM layers, of course, it'll depend on the problem at hand and the specific characteristics of the data, right? So it's important to just experiment with different configurations and see. But overall, at least from literature, what I understand is that if you have a mix of activation functions, they perform better than having a single type of activation functions, because each of these functions have a different ranges and gradients, so they can catch different aspects of the model. So always having different functions, they will kind of capture the different complexities that are there in your data set, right? So that always benefits. But of course, you have to experiment which one works for your specific data set, because each data set has its own characteristics. So it's good you guys tried with different experiments and seeing how that works. But that's the general observation, that having different kinds of activation functions generally captures more, but also there is a risk of overfitting, right? Because then you're overfitting. If you have too many different types of activation functions, they're catching too many different things, and maybe they catch noise, right? So we have to be a little careful when we also do that, when we're doing different activation functions, that we kind of balance it out or use a regularization or dropouts, things like that. So keep that in mind when we're using that.
I have a question.
Thank you.
Sorry. Yeah, go
Go
ahead.
ahead, please.
Oh, I have a question for Vishu. Thank you so much for the presentation. So actually, I think you mentioned a couple of days ago, like in the channel, is like if you just run a single cell of the model and then the accuracy gets better, right? I'm just thinking like, but does that mean like if you run like for infinite many times and then the accuracy is just gonna go like, higher and higher and eventually get to like 100%? Or is there gonna be like an upper limit?
No, there is always an upper limit. Like there is a concept called vanishing gradient, exploding gradient. When you run that same algorithm once or twice, of course, the accuracy increases by some amount. But when you keep running that particular algorithm infinitely, there comes a point when the weights do not change by the backpropagation method. So yes, for once or twice, the accuracy increases. But after some point in time, the accuracies become stagnant. So that is what we call as a breakpoint.
What is the thing you mentioned? Is like, can you say it again? It's a gradient, something gradient?
Yes, vanishing gradient, where you can say like the weights, they do not change much, they become stagnant. And one thing is called the exploding gradient, which we do in the first run, like the weights change drastically, so there's a change in accuracy. So these are the two things which are, you can say, like the vanishing gradient and the exploding gradient, which comes into practice when we are running one model again and again.
I think Kseniya also showed a graph, right, where it's like it drops drastically in the first few epochs and then it kind of saturates, right? So that's something that here. So you can see your losses, right? So they drastically drop in the beginning, and then they kind of saturate.
Yes, like in the graph in the first half phase or the first quarter phase, you see is the exploding gradient. Like the loss suddenly drops. And when we say that the loss is dropping, we mean the accuracy is rising. But in the later phase, you can see that the accuracy becomes almost stagnant. So we term it as the vanishing gradient. Like the gradient is slowly becomes stagnant, and the model is slowly, you can say, reaching its maximum limit for the accuracy.
Okay, makes sense. Thank you.
Yes, thank you.
Any other questions?
I had a couple of questions. Oh, sorry.
Please go ahead. Yeah. We
Go
have
ahead. I
had
just
so-
all the questions, so no worries. Go for it.
Okay, can I go ahead?
Yeah, sure.
Okay, so I had a couple of questions for Vishu and a couple of questions for Kseniya as well. Kseniya, I'm going to start with you. I saw your Excel sheet where you did, the literature review, and then you provided some information on which model to choose. Can you perhaps explain or tell us why we chose like an LSTM over any other time series model? And for Vishu, I had a question about we work with very few features, right? So what was your thought process in like selecting? I think they were just environmental features, if I'm right. That's what was written in the notebook. So why did we choose that? And what did you do about outliers? Like, how did you handle them? Because I remember there were some, mostly for the El Nino thing, which we ended up deleting anyways. But how did you handle the outliers for the other columns?
Yes. So regarding that, how we handled the outliers, we scaled them down. And then we perform the PCA. So when we perform the PCA, and you can say when we got these 6 features which were highly dependent on this particular model on the target variable temperature, these features did not have that many outliers. So simply standard scaling them or min-max scaling them or normalizing them served the purpose. So regarding the outliers question, there was not much thing which needed to be done because the columns which had too many outliers, they were not even taken for the consideration because they didn't even significantly had any significance, or they did not change the temperature that much as compared to the ones which we have taken. So this all deduction was made by feature extraction and the exploratory data analysis.
Thank you. And Kseniya, do you mind telling us why we
Sure,
chose
sure.
LSTM over the others?
Sure. We chose LSTM because it is the most popular model from publications from the publications which consider this problem, this temperature prediction problem, and these publications have good results for LSTM. But I'm not sure that it's quite excellent. But we decided to try LSTM, and we also considered SVR support vector regression, but we got not good results for them, and we discussed this and decided to move further with LSTM, and we were limited at time, and we just worked on LSTM. Probably it would be good to try other models. I saw that some people used also bidirectional LSTM, but we learned, and this not so fast process, and that is why we use only LSTM in our challenge.
Thank you, Kseniya.
Yes, thank you.
Yeah, I think this is also, since it's very popular in handling long-term dependencies, right? And we are also trying to predict this long-term weather, right? 14 days is considered long-term in the weather climate arena, right? So this is kind of it can handle long-term dependencies and kind of sequential data. So that's why it's popular. And of course, there are other models too, but I think we had to pick and go with one. And I think the team did try other models as well, and they didn't work out as well. Sometimes it's also just, seeing what others have done and seeing which ones are popular and start. It's a good starting point, great starting point to go and learn for yourself as to what works and what does not work. But generally, yeah, we do end up trying a few models and seeing which one works best. So there can be other approaches that people have taken. Actually, for the widths, there is a competition. You go to the website and see people have explored a ton of models for this. So that way you can look at other models and compare and see what they have done. So that'll be a good thing to go and take a look. They have a website on Kaggle where the people have posted different models. And I would like the team to post our results too, because we got some good results. So maybe we can still post a notebook even if we don't enter the competition. So yeah, we'll see. We'll see. I'll talk to the team about it in Slack, what we can do.
Thank
Any
you,
other
Xtreme.
questions?
And will the Slack channel, you said the Slack channel will be open, but I
Yes.
see a timer like at the bottom of the page saying that it's going to be active for like 2 more days or something.
Is
I
that-
was wondering if that's true.
Okay, let me check. Let me check.
It's possible that it's specific to my account because I don't have a paid version, so it
No,
might
I mean,
not let me
none of this
access
is
it.
paid.
Or
So none of this is, these are all free accounts on Slack. So they have some limitations, but these are all free accounts. Let me check into that. It should be open, or because I set up the Slack. So let me check. I don't think I put in any time limit, but let me check into that. Good. Thank you for bringing that up. I did realize that was going on because I don't see it from my side, so I don't know. But yeah, I'll keep it on. Yeah, if you want to go and explore more stuff, feel free to do that. We won't be having the weekly meetings though, but I'll always look at the Slack and people can continue the interaction and look at things and learn more. Please do so. That's what it's.
Can we also
Thank you.
share the presentation in the Google Drive?
Yes. So I'll put up the presentation and I'll put up the recording on our YouTube channel and I'll send you a link. So you'll have everything. And then of course the code will be available in GitHub. Right now the GitHub repo was kept private because some people were planning on submitting it to the competition. So we can't have it public. But as soon as now that it's done, the repo will be public. So all the code that the team has developed will be over there and it's open. So you can always go and take a look at it and copy the repo and work from there or something. So it will be open. So it's public.
Do you mind sharing the repo in the channel? I don't even think I'm added to the repo.
So it's not the addition. I think I only added people who were actually contributing to the repo. So if you are, then let me know. I will add you because it's just a lot of overhead for me to manage a lot of people in the repo. So I just limit it to people who are actually putting something on it. Otherwise, it's open to anybody, right? So if you want to look at it's a public repo. So you can always look at what the team has put up over there in terms of code.
Okay. Do you mind just share the name? Because I don't even know what's the name. So even if it's public, if I don't know the name, I can't find
Yeah,
it.
I think the repo, let me share this. Let me stop this first. And let me pause.